Okay, 10.4, inverse matrices and matrix equations. Okay, consider a real number like 7. Does anyone know what the multiplicative inverse is of 7? Multiplicative inverse. So what do I multiply to get 1? 1/7 is called the multiplicative inverse. Then we have the multiplicative identity. So 7 times what makes it unchanged? What number is that? Yeah, 1. Good. So 1 is called the identity element, the multiplicative identity. It turns out these are nice properties for other things, and we're going to use these properties for matrices. So the first thing I would say is, what is this magical thing that if I multiply matrix by it, I get the same matrix back? Okay, so this is called the identity element, and that identity element, we'll call it I. And I'm just going to tell you, it's 1 down the diagonal and 0 everywhere else. Do you believe me? Yeah, what's your favorite number? 3, 5, any other favorite numbers? Any others? -40. Okay, what's the identity of a 2x2? It's going to be another 2x2 matrix, 1 down the diagonals. So do you believe if I multiply this, I'll get the same matrix back? Okay, let's try it. What do I get here? 1 times 3, 0 times 2. I get 3, right? Okay, 1, 0 times 5, -40. 1 times 5 plus 0 times -40. And we get 0, 1 times 3, 2. 0 times 3 plus 1 times 2 is 2. And finally, 0 times 5 plus 1 times -40. And we get -40. Do you believe now? Multiply by identity, we get the same thing back? Okay, and this works for 3x3s, 4x4s, and so on. Okay, and the order matters for matrix multiplication. Turns out if I do in the opposite order, I get the same thing back. So let me write down I2, we just wrote, is 1, 0, 0, 1. Can anyone tell me what I3 is? It's a 3x3 matrix, the 3x3 identity. So what would that be? 0, 0, 1. So I can multiply that by any 3x3 matrix, and it will remain unchanged. Yeah, I4. I'm not going to write it, but it goes on, right? So the multiplicative identity has this nice property. If I multiply it by a matrix, I get the same matrix back. And even if I flip the order, I still get the same matrix back. I didn't do the other way, but matrix multiplication is not commutative, so that's a big deal that I can multiply in any order. Now, to come up with multiplicative inverse, what do I multiply by to get the identity elements? Instead of getting 1, now I want to say, what do I multiply my matrix by to get the identity matrix? And we call this the inverse. A inverse, it looks like it has an exponent -1. That just means the multiplicative inverse. It's not an exponent. Let's talk about the procedure. How do you find this inverse? It's actually super unintuitive. You're going to make an augmented matrix with A on the left-hand side and the identity on the right-hand side. And then you're going to do row operations. Does operations have 2 P's or 1? Operations. Does anyone know what RREF means? You want to get reduced. How do you know? Reduce row echelon form. Okay, so what that means is we're going to get the identity on the left-hand side, and what we end up with on the right-hand side is going to be the inverse. Then we need to interpret the answer. So there's going to be two scenarios. If you actually get the identity on the left, what that tells us is that the inverse exists and it's on the right. But it turns out sometimes you can't get the identity on the left. You might get a row of all zeros on the left, in which case the identity is impossible to get on the left. And we say the inverse does not exist. Okay, let's go ahead and try that. I want to write this in the form of A. And since A is a 2 by 2 matrix, I'm going to use I2. So if we augment that, I'm going to write 1, 4, 2, 10, a vertical line, and then I'll write the identity 1, 0, 0, 1. Are there any questions about this? So now you're all super good at row operations. I want this number to be a 1. It is. And I want to make this number a 0. Very good. -2 times row 1 plus row 2. And I'm going to replace row 2 with that. How much work do you like to show for this? Can I just write the answer, or do you like to see the in-between steps? The 1 and 0 also, yeah. Maybe I'll write -2 times row 1. So -2 times row 1, -2, -8, -2, and 0. So if I add these, -2 plus 2 is 0 like we wanted. -8 plus 10 is 2. -2 plus 0 is -2, and 0 plus 1 is 1. So it's a lot more work because it's twice the size, right? So the goal is to get the identity on the left-hand side. So I really want this to be a 1, and I want this to be a 0. So 1/2 times row 2, and replace row 2 with it. 0, 1, -1, 1/2. Any questions about this so far? I'm going to go ahead and use the 2 to get rid of the 4 right now. So how can I use this 2 to get rid of that 4? Yeah, row 1 minus 2 row 2. So -2 row 2 would be 0, -4, 4, -2. And if we add 1 and 0, we get 1, 4, -4, we get 0. Great. I got the identity on the left-hand side. That means I have an inverse. 1 plus 4, is it? So I multiplied by the -2 so that I could add. But if you multiply by the +2, then you would have to subtract. And then 0 plus -2 is -2. Okay, so what we have here is the identity on the left-hand side, and this is the inverse on the right-hand side. A inverse is equal to 5, -2, -1, 1/2. It's rare that Professor Al doesn't make a mistake, so how could we check and make sure? Yeah, so we could do A times A inverse and check, do you actually get 1, 0, 0, 1? And you have to do actually the other order also. You get 1, 0, 0, 1. But only if you have plenty of time, because that's a lot of work, right, to multiply these. Let me check my notes. Yeah, that looks right. Would you like to see a shortcut? Okay, so this only works for 2 by 2 matrices. What's the formula to find the inverse of a 2 by 2 matrix? Okay, we go through the same process. Let's say matrix A is equal to A, B, C, D. So we have those 4 locations. Someone went through this process and writing A, B, C, D with the identity 1, 0, 0, 1, and did all those row operations till they got the identity on the left-hand side and this magical thing on the right-hand side. And this formula is 1 over AD minus BC, D negative B negative C, A. So this is a shortcut if you want to memorize a shortcut. If I ask you to find the inverse of 2 by 2, you can do either method and get full credit. For this problem, let's go ahead and check. What were A, B, C, and D for our matrix? 1, 4, 2, 10. Okay, so the inverse of this should be 1 over AD is 1 times 10 minus BC, 4 times 2. What's that? Yeah, 1/2. That's right, 1/2. Any questions about that so far? Then we flip these numbers, A and D, to make it 10 and 1. And you make these opposite sign. -4, -2, -4, -2, 1. How do you multiply a matrix by a number? Multiply every number by 1/2. So 5, -2, -1, 1/2. We got the same answer. All right, any questions about this so far? Find the inverse of a 3 by 3. We don't have a formula for this. It would be crazy. Yeah, it would be harder to memorize it than actually to do the procedure, probably. So let's go ahead and find the inverse of this matrix. Augment A with the identity of a 3 by 3. So that would be 1, 1, 4, 2, 3, 6, -1, 2. And the identity is 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, I want this to be a 1. And I want to make these numbers zeros. So -2 row 1 plus row 2. I'll keep row 1 as it is. So 1, 1, 4, 1, 0, 0. All right, so -2 times row 1 plus row 2 gives us 0, like we wanted. 1, -2, 1, 0. That looks like a good idea. Row 1 plus row 3 would give us a 0 for the first number. Oh, awesome. A 0 for the second number. 6. And what are my last three numbers? 1, 0, 1. Very good. All right. Any questions so far? So what do I want to do next? I want to get 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the goal, right? These all look good so far. I need to use this to get rid of that. Row 1 minus row 2 would give me 1, 0, 6, 3, minus 1, 0. I want this to be a 1, so maybe I'll do 1/6 row 3. 0, 0, 1, 1/6, and I'll keep row 2 as it is. 0, 1, -2, positive 1, 0. Now it remains to use this 1 to make these zeros. So -6 row 3 plus row 1. Unfortunately, fractions will not always be avoidable in these problems. 1, 0, 0. Then I have 3 minus 1 is 2, minus 1, minus 1. In the middle column, I like to do 2 times row 3 plus row 2. So 2 times row 3 is 1/3 minus 2. So that would be -6/3 plus 1/3 is -5/3. 1 plus 0, and then plus 1/3. And row 3 will remain the same, 0, 0, 1, 1/6, 0, 1/6. Are there any questions about this? So our inverse matrix is this matrix on the right, which is 2, -1, -5/3, 1, 1/3, 1/6, 0, 1/6. All right. Any questions about this? Yeah, I'm not going to check that I got this right, because multiplying 3 by 3s is a lot of work, right? Any questions? Okay, a note, only square matrices have inverses, but not all square matrices have an inverse. This is a really important point. We call a singular matrix is a matrix that does not have an inverse, and a non-singular matrix has an inverse. From example 2, is that a singular matrix or a non-singular matrix? Yeah, I found the inverse, therefore it is non-singular. Example 3. Do you think this one has an inverse or not? No, probably not. I want to show an example of one that doesn't have an inverse square matrix. Okay, so how do we find out? Okay, I look for an inverse, and I'm going to get a row of all zeros. 1, -6, 4, 3, 4, 2, 5, 3, 5. I augment it with 1, 0, 0, 0, 1, 0, 0, 0, 1. What should I do first? -3, row 1. Add it to row 2. Hang on a second. I can only process so much at once. Okay, -3, row 1 plus row 2. Just so I don't make mistakes, I'm going to write -3, 18, -12, -3, 0, 0, and add them. -3 plus 3 is 0. 18 plus 4 is 22. -12 plus -3 plus 0, 0 plus 1, and 0 plus 0. Double, triple check, because if I make a mistake, I might make it invertible by accident. Okay, what was the other thing you said? -5 row 1 plus row 3. So I'm going to write -5 row 1 below here. -5, 30, -20, -5, 0, 0. And I'm going to add all of these together. So -5 plus 5 is 0. 30 plus 3 is 33. 5 plus -20 is -15. -5 plus 0, 0 plus 0, and 1 plus 0. What should I do next? Okay, notice that these have a common factor, 11. So I would really like to make one maybe, well, what's the easiest way to make these opposites? There's infinite ways to do it, but what seems easiest? All right, yeah, get them to 66 would probably be easiest. How do I make the green one equal to 66? 3 times row 2, and then I want this to be -66, right? So I want to multiply this by 3 and this by -2. So -2 row 3. That looks like there's a lot of potential for a mistake here. So I'm going to write these down. 3 times the green row would be 0, 66, -30, -9, 3, 0. And -2 times the second row, or the third row, sorry, is 0, -66, 30, 10, 0, -2. And so if I add those together, I get 0, 0, 0, which is what gives me that it's non-invertible. But let's go ahead and continue this. 1, 3, -2. And I'll keep row 1 and row 2 the same. 1, -6, 4, 1, 0, 0, 0, 22, -10, -3, 1, 0. Okay, so if I have a row of all zeros, it makes it impossible to get the identity. So row of all zeros on the left implies A inverse does not exist. So we say that A is a singular matrix. Any questions about this? So why do we care if matrices have an inverse? It helps us solve matrix equations, which helps us solve systems of equations. So I'll just rewrite the same thing on the right-hand side. If I have matrix A times a variable matrix is equal to a solution vector or matrix. So X is a variable. Remember, the capital letters at the end of the alphabet are variable matrices, meaning they're unknown. All entries are unknown. The capital letters at the beginning of the alphabet, A and B, means all those numbers are known. They're constants. So if an inverse exists, I can get the variable by itself by multiplying both sides by the inverse of A. Okay, I made a very subtle mistake. What mistake did I make? The order matters. If I multiply by A inverse on the left, I have to multiply by A inverse on the left on this side also. Because matrix multiplication is not commutative. Get a different answer. Okay, what is A times its inverse, assuming it exists? The identity. What's the identity times any matrix? It's the matrix unchanged. So it turns out if you find an inverse, we have a shortcut to find the variables. You do A inverse times the matrix on the right. But make sure you multiply by the inverse. Must multiply by the inverse on the left. Let's go ahead and apply this to example 4. So first we're going to write this as a matrix equation. Rewrite as a matrix equation. So I'm going to write it as a vector on the left, 3x minus 5y, and 2x minus 3y is equal to the solution vector, negative 18, negative 11, or we also call that a column matrix. Okay, this is a tricky thing, is we're going to take just the coefficients, 3, negative 5, 2, negative 3, and we're going to multiply by vector xy. Can you verify for me that this is okay? If I multiplied this, I would get 3 times x minus 5 times y. Yeah, and if I multiplied this, I would get 2 times x minus 3 times y. Okay, so this is the tricky thing. Can you translate this equation into a matrix equation? If you can, then we have the form we want. A times the variable matrix is equal to the solution matrix. So what is the answer? The answer is A inverse times B, assuming this exists. Let's find the inverse of matrix A. Do you want to use the shortcut? A inverse would be equal to, well, I have a fraction, right? I'm going to write the formula again, just to remind you, AD minus BC times D, negative B, negative C, A. So in this case, we would have 1 over, what's A times D? 3 times negative 3 is negative 9, minus, what's B? Negative 5 times C is 2. And then that would be negative 3, 5, negative 2. Are there any questions about this? 1 over negative 9 plus 10. Is that just 1? Okay, so A inverse is equal to negative 3, 5, negative 2, 3. We found the inverse. Someone asked, does this always work? Sometimes this matrix is non-invertible. So how would I know if the matrix is non-invertible? If this denominator is 0. Okay, so my answer, my solution matrix, matrix X is equal to A inverse times B. Or in other words, XY is equal to negative 3, 5, negative 2, 3 times my solution matrix is negative 18, negative 11. So we just need to do this multiplication. negative 3 times negative 18 plus 5 times negative 11. And then we'll do the second row times that column would be negative 2 times negative 18 plus 3 times negative 11. So that gives us 54 minus 55. 36 minus 33, negative 1, 3. So our solution is the ordered pair negative 1, 3.